So, good afternoon, everyone, and welcome. Thank you for joining the New Zealand Society of Earthquake Engineering webinar. Today's session is on seismic restoration of three-story URM CAPS building. Is presenting by Sean Gardiner. Sean is a Christchurch-based structural engineer and a senior technical director at IGIS. Before we begin, I would like to share a brief introduction about today's presentation. Sean present this talk or a version of this talk at the recent New Zealand Society of Earthquake Engineering conference in April in Wellington, where it received the Best Practice Paper Award. Congratulations again. For this project, Sean provided technical oversight, undertook project review, and was ultimately responsible for the work as a produce statement author. He would also like to acknowledge the significant contribution of James Carter, Clara Caponi, Andrew Iden, Peter Comoke, and others who play a key role in the project's success. It is really wonderful. Sean is presenting this work today, sharing it with a wider audience that other than who attending the conference. We almost 160 people registered, which is fantastic to see that. And I just want to just say that I would appreciate if you submit your, if you have any question or comments, submit it in the QA in the top of the team meeting and not in the chat, so we can manage better the question or comment. And yeah, Sean, over to you. Thank you.
Thank you, Niku. Good afternoon, everyone. I'm Sean Gardner from Aegis. I'd like to start by particularly acknowledging my co-authors for the paper that accompanies this. So Clara Caponi and Peter Kamek, both who also work with me at Aegis, for their content and contributions. Today I'm presenting the seismic strengthening of the Consumer and Applied Sciences building at the University of Otago, a three-storey unreinforced masonry building originally constructed in 1918. Before getting into the building itself, I want to spend a few minutes, I guess, framing the problem, because whilst this is not a typical commercial strengthening project, unreinforced masonry or URM buildings like this generally share a number of fundamental issues. First, they don't tend to behave as structural systems, rather as a collection of elements. Second, they typically have very poor connectivity between the walls, between the floors and the walls or the roof, and even between the walls themselves. And third, they're made up of materials with very different properties, generally relatively strong masonry units with relatively weak mortar. So in an earthquake, instead of distributing loads and deforming in a controlled way, the building tends to come apart, which is why a large part of the focus for these types of structures is reliably tying them together, with in-plane strengthening, if necessary, coming afterwards. This project was part of the University of Otago's redevelopment program that started around 2019. The building itself is a three-storey unreinforced masonry structure, as I mentioned, constructed around 1918, and importantly, it's a Category 1 heritage building forming part of the university's Gothic precinct. From a seismic perspective, it was assessed at less than 15% MBS, so clearly earthquake prone and required intervention to enable the ongoing use of the building. Though the key challenge here wasn't just strengthening, it was doing it in a way that retained the heritage, fabric and architectural character. From the outset, the project was about balancing seismic performance with preservation. So the building itself, CAPS for short, but Consumer and Applied Sciences building, is located at 89 Union Place in Dunedin. Three-storey unreinforced masonry comprising a ground floor First floor and second floor, all constructed in timber. The building is rectangular in plan with an approximate footprint of 30 metres by 16 and is listed on the Historic Places Trust Register at number 325 as a Category 1 building. Building is founded on no fines concrete strip foundations with suspended timber floors. The external wall comprises bluestone, otherwise known as vesicular basalt, in an ashlar form, which is the ones with the squared blocks and the even pointing, with dressed Oamaru stone or limestone used for the architectural elements, while the internal walls were plastered. The wall construction varies with height, transitioning at the attic floor level to masonry, to limestone masonry on the inside with a reduced cavity, while the external bluestone veneer remains continuous. A small basement in the middle of the floor plate, it's actually underneath here, houses the boiler room and is constructed with a concrete slab on grade and concrete retaining walls supporting portions of the ground floor. Internal load-bearing walls, again around through here particularly. Consist of 2 or 3 brick wides, or consisted of 2 or 3 brick wides, resulting in overall wall thicknesses of around 215 or 330. The ground and first floors are timber framed, supported by the masonry walls, timber bearers. At level 1, there's also some steel. There were some steel beams and shallow concrete piles at the ground floor level. The roof comprises slate tiles supported on timber sarking and rafters. Deep timber trusses support both the attic floor and the roof, with transverse trusses bearing directly on the perimeter masonry walls and longitudinal trusses supported by transverse members. Steel ties and brackets provide localized truss connections. Gable walls comprise limestone masonry supported on concrete lintels over window openings with brick piers providing support. Given the age and construction of the building, we couldn't rely heavily on the original drawings or assumptions, so detailed visual and intrusive site investigations were critical. We undertook intrusive investigations, opening up the floors to confirm their construction, the span of the joists and their connection details into the walls and to the steel beams. There was stripping of wall linings to determine the brick bond arrangement, and we also took core samples to verify the wall makeup and for material testing, all to understand how the building was actually put together. What we confirmed was a multi-withe wall system, an external bluestone veneer, an internal brick leaf, and a rubble-filled cavity between them, with essentially no positive connection between the layers. The room layouts and general dimensions aligned with the drawings, and the wall locations were able to be confirmed. Internal wall thicknesses were measured. There were minor changes to the masonry walls where new openings had been cut, new door openings had been cut, and some old windows had been infilled. We also confirmed that the timber floors were simply pocketed into the walls with limited connection, only about 50 millimeters of bearing, so not providing any meaningful diaphragm restraint, though we found the flooring was thicker than expected, generally consisting of 2 layers of tongue and groove. Diagonal 140 by 25 boards, actually you can see them here, and straight 90 by 20 boards over. Material testing undertaken by Desir Consulting showed reasonably strong brick, but weak lime mortar, which is fairly typical for buildings of this age. Salt testing was also carried out by the stone company, and that indicated that while salt was present in the walls, it was below 0.5% by weight, which is generally considered the level at which it may start to cause damage to stonework. Overall, these investigations gave us a much greater confidence in the load paths and behaviour, and in a building like this, small details can significantly influence the governing failure mechanisms. The detailed seismic assessment confirmed the building was well below 15% MBS, and more importantly, it clarified the key vulnerabilities. The most critical issue was the lack of composite action in the external walls. The different wides were essentially acting independently. The cavity material consisted of loose, no fines concrete with a high ratio of voids. Earthquake shaking could induce consolidation and migration or shakedown of this material under gravity, leading to the onset of bulging issues. This increases the disconnected nature of the wall fabric. This leads directly to the governing failure mechanism, which is out-of-plane instability, particularly bulging and eventual loss of the external veneer during shaking. In addition to that, the diaphragms were weak and flexible, and there was very limited connection between the floors and walls, so poor load transfer throughout the structure. There is a high proportion of openings and penetrations, particularly to the end walls, limiting the building's in-plane capacity there. The building geometry favours the onset of local failure mechanisms, for example, the gable end walls and slender piers, and the interdependency of the in-plane and outer-plane responses can lead to progressive weakening of the building structure. So overall, the building lacked a reliable load path, both in-plane and outer-plane, which is typical for this type of construction. This, I guess, indicates where some of those localized failures would be expected to occur. Both outer plane and in plane. So before jumping to solutions, we defined some key objectives. We needed to increase the building's seismic capacity to a meaningful level. This inherently reduces the risk of significant damage or collapse, therefore increasing the chance of its longevity, and also increased chance of repairability in the event of an earthquake. We needed to retain the heritage fabric, particularly the external stonework. We wanted to achieve a system that would perform in a controlled and dependable way during an earthquake. We weren't just trying to make the building stronger, we were trying to improve how it behaves. So we did this by consolidating the perimeter walls to avoid material failures, by increasing the outer plane capacity, by increasing the in-plane capacity, and by ensuring that the diaphragms and connections can tie the building together to distribute the earthquake forces. So looking at some options, we considered a wide range of strengthening options, and at first glance, many of them were technically viable. But when you look closely, the trade-offs become quite significant. All the options require full wall consolidation. This involves injecting a lime-based grout. We used Mape Antique into the walls and installing ties to connect the wides together. From a heritage perspective, this is very attractive because it retains the original fabric. Post-tensioning was looked at. This introduces compressive forces into the masonry using cables, strands, or rods, improving stability and performance without adding new lateral systems. So you can see on the right-hand image there, this is the original structure, options with kind of external post-tensioning and internal post-tensioning. Separately, the gables were addressed in the concept options by the use of strong backs, which I haven't shown here. We also considered steel brace frames. These can provide excellent seismic performance, but they can introduce stiffness incompatibility. The frames are relatively flexible compared to masonry, so the masonry may still crack before the frames engage. They also require new foundations and significantly alter the internal space, and could well have required piles. Another option that was considered was a reinforced concrete core. This is structurally very efficient, but fundamentally changes how the building behaves. It also requires extensive demolition, temporary works, and new foundations. As I'll go into when I look at the adopted solution, whilst concrete wasn't used, we did end up replacing the internal walls with reinforced masonry, which has some similar characteristics to this, but also utilised the post-tensioning and the exterior frames. We also considered shotcrete strengthening. While this can increase the strength, it raises concerns about durability, particularly moisture being trapped between materials and degradation of the heritage fabric, and it's largely irreversible. Finally, we considered timber options, but they have challenges around deflection compatibility and limited structural benefit. So when we evaluated these options, we weren't just looking at strength, we were looking at compatibility, constructability, heritage impact, durability, and costs. The strongest solution is not necessarily the best solution, I guess was the takeaway here. But it certainly allowed us to help the client to look at the options that were likely to be most feasible for this structure. The final solution was based on three main components working together. First, wall consolidation. This involved injecting a lime-based grout into the walls to fill voids and improve cohesion. We also installed a grillage of stainless steel ties at regular centres to connect the wires together. The goal here was to create a composite wall, effectively turning three independent layers into a single structural element. It also mitigated to some degree the variance in through thickness wall stiffness when we were applying the post-tensioning, the vertical post-tensioning. Second, post-tensioning. We installed both vertical and horizontal post-tensioning elements. You can see these were applied. The vertical elements were only on the ends in the middle of the walls. Horizontal was applied to the perimeter. The vertical tendons improve the stability of the wall piers. The horizontal tendons help restrain the wall spandrels and ensure a pier rocking mechanism rather than potentially rocking at the base of the piers and damaging the spandrels. It also helps to distribute loads throughout the diaphragm. Overall, the system introduces compressive clamping forces, which improves both in-plane and out-of-plane behaviour. What's important about this approach is that it enhances the existing structure rather than overriding it. The third element was diaphragm strengthening. The timber floors were upgraded using plywood sheathing and steel drag ties. This creates a more reliable load path and allows seismic forces to be distributed across the building. In addition to that, the internal load-bearing walls were replaced with reinforced concrete masonry. This was necessary because strengthening the existing walls couldn't achieve the required performance. Essentially, actually I might even have it. Yeah, the walls that were located in and around the core here, we looked at options using FRP as well as post-tensioning, but couldn't get the significant inertial mass associated with the tributary area of the middle of the building to get these walls to work. So that's why they were replaced with reinforced masonry. And the perimeter walls left to support their tributary areas. Overall, the strategy was to retain and enhance the external structure, introduce targeted improvements where needed, and create a more unified structural system. You can see here that some of the details associated with the exterior horizontal post tensioning and the extent of the diaphragm strengthening. A new lift was also introduced. The original stairs were retained. This is the attic floor, which shows where the deep attic trusses were located. From a construction perspective, the project presented a number of challenges. The building was fully scaffolded and encapsulated to allow works to proceed while protecting the heritage fabric from the elements. The grout injection required careful control. Some testing was done early on in the process to measure the volumes that would be required to estimate, to assist with pricing, but also to estimate the volumes that would be required throughout the project. In some areas, though, grout would flow through unexpected voids or appear externally, so that required continual monitoring and adjusting throughout the process. Post-tensioning installation required a high degree of precision, particularly for the vertical tendons. Alignment over the full height of the walls was essential. Internally, replacing the load-bearing walls required staged demolition and extensive temporary propping. And finally, the project was delivered in stages using 2 separate contractors, which introduced coordination challenges, particularly the requirement for new diaphragm penetrations. So one contractor was responsible for the seismic strengthening and the second was responsible for the fit out. Unfortunately, the fit out then wanted a whole bunch of holes everywhere. One of the most significant incidents occurred during the fit out stage where a post-tension tendon was inadvertently cut. So if I go back a slide, I think it was one of these piers down here when they were coring without asking through the pier. They went straight through one of the tendons, which obviously made it ineffective and required the bricks to be locally removed, a coupler to be installed, and the tendon to be retensioned. Well, that temporarily reduced the capacity of the building. There was no immediate life safety risk, but it clearly demonstrated how critical those systems are. It also highlighted the importance of maintaining control over the structural system throughout construction. These are some of the images. The top of the top concrete beam prior to it being poured. This is where the vertical tendons were anchored. This is the end of the horizontal post-tension. The vertical bars were stainless steel McAlloy bars. The horizontal ones are stainless steel post-tension cables. Hopefully this will work. This is tensioning of the cables. As I mentioned, there were some challenges with the stage delivery process that was adopted. You can see on the right, this particular contractor went to town on trying to find I don't know what they were doing, but cutting a pier to pieces, and that middle one there was where the strand was, the cable was. Obviously, the introduction of new penetrations into a diaphragm that's previously been strengthened requires additional trimming members, so a lot more work than if it had been considered from the outset. There's also fire rating issues as well. However, the building strengthening and fit-out works were completed. I guess some credit to Cook Brothers here for their the photographs that are presented here. In terms of key takeaways, the detailed seismic assessment confirmed that the building was earthquake prone at less than 15% MBS, with resilience limited by poor wall composite action and subsequent in-plane and out-of-plane capacity, inadequate diaphragms, and insufficient wall-to-floor connectivity. Early intrusive investigations and material testing were fundamental to understanding actual construction material variability, load paths, and system behavior, providing a reliable basis for resilient seismic design. Slight changes in design parameters can have significant effects on the results and potentially change the governing mechanism. Strengthening options were evaluated not only for strength and stiffness, but for their ability to deliver robust, compatible, and repairable seismic performance while minimizing heritage impact. Consolidation of the masonry walls combined with post-tensioning and strengthened timber diaphragms was adopted to promote a unified structural response, controlled damage, and post-event repairability. Construction methodologies incorporating testing, verification, and careful sequencing to ensure the intended seismic load paths and resilient objectives were achieved in practice. The staged delivery highlighted that seismic resilience is highly dependent on effective coordination, knowledge transfer, and protection of completed strengthening works during subsequent construction stages. It's important to ensure the project has adequate budget and program allowance to enable well-coordinated, robust solutions that support resilient seismic performance and avoid compromising long-term outcomes, as elegant solutions take time to develop and integrate with the existing building fabric. And finally, construction sequencing and coordination are just as important as the design itself in achieving the intended outcome. I guess as a final note, in the last couple of weeks, I understand the building is now called the Annie Stevenson Building, formerly CAPS, and it was entered in the Property Council Awards and received a merit in the Heritage and Adaptive Reuses category. We had some kind words from the client. This recognition highlights the hard work and care that everyone put into the CAPS project as we sought to retain the building's heritage fabric while ensuring long-term safety and usability. The building, recently renamed the Annie Stevenson Building, now supports a modern, flexible, shared office environment for staff on our campus. Thank you.
Thank you, Sean. Thank you, Sean, for a very excellent presentation. It's very great to see that this historic heritage building coming back to life. Now is it time for the QA? I couldn't see any question right down in the QA, so maybe I open for the papers as if they want to have if they have any question or comment, just now mentioning of that and talking about that. Yeah. Any question or comment? Okay, looks like no. So, yeah, we have.
Bravo's got one in there. Great project. You mentioned there is a balance between earthquake performance and heritage. Was the expected resilience in design earthquakes assessed? Not specifically. We were, I guess, inherently the building was stronger and so therefore less likely to catastrophic collapse. It is still brittle materials that will crack, and there will be redistribution. And if it got to the design level that we were targeting, where the piers were still rocking, there would still be damage, but the chances of repairability are much higher. I'm trying to keep a track of things. Do you want me to just work my way through them, Niku?
Yeah, I would appreciate. Yeah, since we have about 5 more questions.
How was the grout selected, and how was effective void filling confirmed? So the grout that was adopted is Mape Antique, which is a mixture of components, but lime based, to be compatible with the existing lime mortar of the stone and the internal brick. There was some testing done. Some cores were, I believe, taken after the testing phase to confirm that the consolidation was complete, and also that the testing obviously allowed us to estimate the volumes required for the construction, or the main construction. What methods were used to analyze the existing building structure? Was this using the method of C8 or more detailed 3D modeling? Mostly C8. The localized, I mean, in some ways, the seismic assessment was relatively quick, in that as soon as the walls were identified as not being able to support themselves, or support significant outer plane loads and were at risk of falling to pieces, as soon as you start establishing, trying to determine the capacity, the outer plane capacity of a single withe, it has very little capacity. In terms of distribution of loads, that was using essentially tributary area. So no further detailed modelling was there. In terms of 3D modelling, I'm not sure what additional benefit that would have had. Perhaps it could have given us some additional capacity or more detailed capacities for the local mechanisms of the gables. But I think they were found to be of low capacity, and I'm not sure that more detailed analysis would have given us much. Any pushback on the external post-tensioning given the heritage strategy? No, I think given the options, I think that was probably one of the more sympathetic options that was available to them. We engaged with Heritage New Zealand throughout the process, and I think they were certainly supportive of the project, and supportive of the adopted solution at the end. I'm not sure, Niku, is the paper publicly available if people want to, I guess, read more? Or you're on mute if you're...
Sorry, I sorted out as a most popular question. So the all of the paper will be, since I'm not sure that it still is available or not, but we will be in the next 2 months, definitely. I now sort out a question based on the vote. So Daniel asks you the question: was the seismic rating evaluated post-strengthening?
Well, not re-evaluated. We targeted the strengthening to be 67% MBS.
Okay.
Well, to achieve at least that, as the diaphragms themselves were designed for loads that are kind of 50% higher than that, but we ensured that the masonry walls in plane could handle the 67% loads.
Chanji asked that, thanks, Sean, how the stress loss in the post-tensioning tendon has been managed and how it will be managed in long term.
The actual level of post-tensioning in the strands is relatively low. We did account for losses, so there was some slight increase in I guess what the design level of stressing was, but given that it's given that it was relatively lowly stressed, we're not expecting significant losses there. If it does rock up, it will still engage. In terms of long-term and I guess post-event checking, they would require uplift. So they need to gain access to the top of the strands, to top of the McAloy bars, and re-grab them to verify the stresses inside them. As was the case for the replacement, this did actually require localized removal of the stonework that covers the concrete beam there, the capping beam at the top of the pier. Grab the top of it, re-check the stress in it, and then rebuild the masonry there.
Thank you. The next question from Lee. That's a great project. How long did the work take and how much did it cost?
I don't know that I know the answer to that. In terms of, I can tell you that it took a long time, and I can tell you that it cost a lot of money, but I don't know the specifics, I'm afraid.
Okay, the next one. Thank you. Interesting project. Was there any investigation prior analysis on the dynamic characteristics of the building before and after the lime grout injection? I understand lime grout is favorable compared to cement grout, but would be interesting to know the impact.
I don't. No specific additional analysis was done looking at the difference between lime and cement grouts, or on the dynamic performance of the piers. I imagine that once it's a consolidated element, it'll perform as a single unit, which was the intention.
Thank you. The next question is thank you for presentation. How were the gable end walls on upgrade to improve their out of plane capacity?
Yeah, so in those locations, so we did a couple of things. We drilled and grouted vertical stainless steel bars into the small parapets that you can see on the image there, to stop them from falling out. There was also a series of steel strongbacks installed against the back face of the gables.
Yeah. Next question is that, is there something designed to achieve 100% MBS, and are the post-tensioning cable material specification and diameter determined based on the PT design requirement specifically to the cable material, strand diameter, and the number of the tendon?
Sorry, that was a lot there.
Yeah.
What was
it some question?
All right, let me see if I can find it.
So maybe I start with the first. It is for the reaching of the 100% MBS. It's retrofit for that.
So we were targeting 67% in plane capacity.
Okay.
The post-tensioning material cables are determined based on the specific PT design requirements, specifically the cable material strand. Yeah, so we had a target stress, we engaged with BBR Contact, who did a lot of the work at the Art Centre, and worked with them around, I guess, available and appropriate materials. I believe it was 25 mil bar, but yeah, it's been a while. But yeah, so certainly we work closely with PT suppliers around making sure that we could get the products that we needed to be able to achieve the stresses that we wanted.
Awesome. The next question is that from Fabrizio, vertical post tension require anchor into new concrete footing. This must have caused quite a significant work and clashing with existing foundation system. Any temporary support required to the outer wall while doing that? Any comments on the construction methodology for that?
Well, I guess, yeah, I mean, it wasn't too bad. They excavated underneath the existing footings, and locally poured new pads to house the bottom anchorage blocks. No temporary works were required. There is a concrete foundation around the perimeter, which allowed it to span over those localized excavations. I don't recall there being any particular concerns. The foundations weren't particularly deep, and the ground was not too bad in terms of its stability. So yeah, not that was probably one of the more straightforward parts of the project.
Okay, great, thanks. The next question is that what out of plane drift limit was used for a strong back design?
An out of plane drift limit.
Do you remember?
Are they worried about the drift, or are they worried about the out of plane? I mean, they were stiff to make sure that they I guess were effective, but I'm not sure that we targeted any specific. As I said, I'm not sure if you're concerned mostly about the deflection between the floors, or if you're worried about the floors leaning out, and as what in conjunction with the wall movement. The overall drifts of the building were established to be pretty low.
And thank you so much. The next question. Did you use the proposed new national seismic hazard model for the design of and strengthening of that, or the current one?
No, I mean, we were getting into the seismic assessment was done in 2019. Started in 2019. The strengthening work, the strengthening design work was only done, would have been done in 2020, 21. So before the release of the latest seismic hazard, national seismic hazard model. So yeah.
Yeah.
We knew something was coming, and this was the best we had at the time.
Yeah, good. Just wanted to mention that this paper will be available. Usually, all of the conference paper available for everybody 6 months after the conference, and also the record of all of the keynote session during the conference will be available in the NZSEE YouTube channel. We have one question in the chat. I say this is Cam. Harshan, once the cavity was filled, did your architecture need to the reinstate of the cavity with an internal partition wall to avoid moisture transfer?
Sorry, once the cavity was filled, there was no. I mean, there were areas where it was already quite well consolidated, and the areas where it was a lot of void. In terms of moisture transfer, the there was no difference. The material is quite breathable by nature, but yeah, there was certainly no tracking of water, and it's not a veneer in the conventional sense where there's a cavity to allow it to drain. These were solid masonry walls.
Thank you. I think it's answer all of the question. Thanks to everybody that's raising of them give a question and they give us the comment. This webinar has been recorded and will be uploaded to the NZSEE YouTube channel. So those who missed the presentation today will be able to watch it later. I just want to also mention that to all of the audience that the NZSEE is pleased to announce that the Pacific Conference of Earthquake Engineer 2027 will be held in Christchurch from 16 to 18 of the February. Abstract submission will be open in early July next week. So add it to your calendar. And the deadline is the 15th of the August. It is wonderful to see you all there during the next conference and to share our knowledge and to continue certain resilience across the Aotearoa, New Zealand. Sean, thank you so much for sharing this presentation during the conference and today for us. And thank you all participants who joined us today. And we really appreciate your participation. Have a great rest of the day. Thank you. Thank you so much.
Thanks, everyone.